Good morning once again. Welcome to Elcom. Last time we looked at how to calculate or determine the ground state time for D4 atomic orbital. Today we want to look at how to determine the ground state time for D3 atomic orbital. So first, you have to write down your angular orbital quantum number values and also the spin quantum number values. So for D3, we know that the L, which stands for the angular orbital quantum number, is 2. Then for the magnetic quantum number, it starts from plus L, 0, and negative L. So in this case, since we have the angular orbital quantum number to be 2, the magnetic quantum number starts from plus 2, plus 1, then we have 0, negative 1, up to negative 2. Then D3, the D orbital has electrons. So considering the spin quantum number, it means that each electron can spin either upwards, which is designated as plus half, or it can also spin downwards, which is also designated or represented as negative half. So after writing down the angular orbital quantum number and then the magnetic quantum number and the spin quantum number, we now write down the orbitals and then fill them with the electrons. So we know the d orbital is a degenerate orbital. So it has 5 orbitals, 1, 2, 3, 4, 5, and they are degenerate. So here we have each of the magnetic quantum number, which is representing each orbital here. Then we fill the orbitals with electrons, the degenerate orbitals with electrons, according to the rules in filling electrons. Here we have to obey all the 3 rules: the Hofbauer rule, we have the Hans rule, and the Pauli's exclusion rule. So according to the Hofbauer, we have to fill from the lowest orbital to the highest orbital. According to the Hans rule, we need to, if we have a degenerate orbital, we need to fill with single electrons in the same spin. Then after that, if we have still remaining other electrons, we add up, we pair them, but we change the spin. But since we have only 3 electrons here, we can only fill with just 3 electrons, 1, 2, 3, all in the same spin. So we obey the Hans rule. We obey also the Hofbauer rule. After filling them with the electrons, then we have to determine the total orbital angular quantum number. So to determine the total orbital angular quantum number, we have to add all the orbital angular quantum number of each orbital that contains the electron together. So since we have electron in this orbital, electron in this, and electron in this, we add them together. So we have the magnetic quantum number of this is plus 2, and then this is plus 1, here is 0. So we have the total to be 3. So the total orbital angular quantum number is 3. We obtain that by adding the magnetic quantum number of each orbital that contains the electrons together. After that, we also add the total spin quantum number. We know that each orbital can spin either in upwards, represented by plus half, or downwards, represented by negative half. Downwards also means that against the field, and this is in the direction of the field. So since we have 3 electrons and they are all spinning upwards, so we represent them by plus half, meaning that this orbital has a spin quantum number of plus half. This also has plus half, and this also has plus half. So adding the 3 together, we get 3 over 2, which is the total spin quantum number. Then after that, we have to determine the term for D orbital. Since we know the total orbital angular quantum number to be 3. Now we check from this. If you have the total orbital angular quantum number to be 0, your term is an S. If it is 1, it is P. If it is 2, it is D. If it is 3, it is F. If it is 4, it is G. 5, H. 6, I. So since we have it to be 3, our term is F10. Then after determining the term, we have to determine the spin multiplicity. So we can calculate the spin multiplicity by using 2s plus 1 formula, where the s stands for the total spin quantum number. We know the total spin quantum number to be 3/2. So we just replace the s by 3/2. So 2 cancels 2, we have 3 plus 1, 4. So we have the spin multiplicity to be 4. So the ground state term for D3 atomic orbital is 4f. Thank you.